Okay, we're going to cover the problems 64 and 68 solutions from chapter 5 in the Survey textbook. 64 says the ball launcher in a pinball machine has a spring that has a force constant of 1.2 newtons per centimeter. Uh, the surface on which the ball moves is inclined at 10 degrees with respect to the horizontal. If the spring is initially compressed 5 centimeters, find the launching speed of a zero point 0.1 kilogram ball when the plunger is released. Friction and the mass of the plunger are negligible. Okay, so first thing we want to do is reproduce the diagram from the book and then begin our energy problem. So I'm going to draw that diagram here offline. Okay, so here we see that the ball is in its initial position before you pull the spring back. Your hand then pulls the end of the plunger back 5 centimeters. So the ball rolls down to this dotted position. So what we're looking for is the speed at this original position when it's launched. When the spring has been released and has returned back to its initial position, we want to find the speed at that location. So we're going to apply our standard method by which we solve energy problems. We're going to say that E is equal to K plus U at any point, and that E at a second point is equal to E at the first point plus any work done in between. So the 2 points that I'm going to identify are the point of the ball as it leaves the spring and the point of the ball when it's completely compressed. These will be my two different energy positions. So E1 is going to equal the kinetic energy at position 1 plus the potential energy at position 1. And so we have to identify at that lowest position, um, before it is released, it has a kinetic energy of 0 because it's not moving. And we're going to define the potential energy to be 0 at that position as well. Actually, no, I don't want to do that. I want to define all of the energy as spring potential energy at that point. I'm going to say that the gravitational potential energy is 0 at that position. Then at E2, the E2 is equal to K2 plus U2, and K2 is going to have some kinetic energy because the ball is going to be moving, and it's going to have some potential energy. It's no longer going to have any spring potential energy, but it is now a distance y above where it started. So it's going to have gravitational potential energy mgy. So since the problem told us that this was a frictionless system, we can say then that E2 is equal to E1 plus 0 for the work. No work was done to friction, no energy was lost, so the two works are equal. So I can say 1 half mv squared plus mgy is equal to 1 half kx squared. The problem here is we need to solve then for v, the velocity of the ball as it is released. So I can go ahead and do some algebra now. So I'll say that v squared 1 half mv squared is equal to 1 half kx squared minus mgy, which kind of makes sense. Here's the amount of energy I started with. Here's the amount of energy that is in the stored in the gravitational field. So any energy that's left over in that difference becomes kinetic energy of the ball. Um, so solving for v, it must equal 2m times kx squared minus mgy, square root of that. Now, do we know all of these pieces? Do we know the mass? Yes, we were given that. So we know the mass. Do we know the spring constant? Yes, but you'll notice the spring constant is given in units of newtons per centimeter, and we need K expressed in newtons per meter. So 1.20 newtons per centimeter is going to equal 100 centimeters per meter times 120 or 1.2 newtons per centimeter, and that will give me 120 newtons per meter as my spring constant K. So I now know K. So I know M and K. And do I know the distance that the spring was pulled back? Yes, X was equal to 0.05 meters. So I know X. I know M. I know G. And I know Y. Well, do I know Y? Again, we have to get Y from our geometry. So here we have this triangle uh, from the inclined plane, a 10-degree angle, and the length of the hypotenuse is 0.05 meters. It was pulled back 5 centimeters, so we can get this height, y. Y is going to equal 0.05 times the sine of 10 degrees because it's the vertical side or the side opposite of the angle. So y must equal 8.68 times 10 to the minus 3 meters. So I can substitute in all of those values and get an answer. 0.241 meters per second. Okay, the next problem we're going to look at is problem number 68. We have a 2-kilogram block resting on a plane um, that starts tied to a relaxed spring. The block is released and it slides down the plane and comes to rest eventually at a new location. The question is, given that the block slides 0.2 meters down the plane, 20 centimeters, and that the spring has a constant of 100 newtons per meter, how large is the coefficient of friction between the plane and the block? So we're going to approach this from an energy standpoint. So again, I'm going to say that E1 is equal to K1 plus U1, and E2 is equal to K2 plus U2, and that E2 is going to equal E1 plus any work done. The new energy is equal to the old energy plus any work done. So these equations will be the foundation of this particular problem. So again, I have to pick two spots, the position for E1 and the position for E2. So E1 is going to be the position when the block starts, and E2 is going to be the position when the block comes to rest again. So at the top of the um, motion, E1 is going to equal, well, the block is at rest when I release it, so the initial kinetic energy is 0, and the initial potential energy is going to be some value. I could choose to call this 0, or I could choose to put the 0 at the final location. I am actually going to do this problem from a standpoint of calling the amount of energy at the initial position as the gravitational potential energy equal to 0 position. So since E is equal to K plus U1 could be gravitational potential energy, which we just decided to call 0 there. And it also can be spring potential energy, because there's a spring in the problem. But the spring is unstretched, so that is also equal to 0. So we are going to say the initial amount of energy in the system is 0 joules. That may seem kind of weird because the system actually moves. It has energy to move. But remember that it's going down in energy, so it's going to negative potential energy, which is perfectly acceptable as a way to generate motion. So now we're going to do the same thing again with E2. E2 is going to equal K2 plus U2. Well, here, again, the system is stopped when it gets to the bottom of the plane, so the kinetic energy, 2, is 0. But now we have potential energy. We have potential energy stored in two forms here. The spring is now stretched, so it's going to equal 1/2 kx squared, the amount that it extends. And the block is also going to have gravitational potential energy, mgy, the amount it has moved vertically up or down. It turns out that y here is going to be related to x. So we really are going to end up with a single variable in x, but we need to figure out how far that distance is. So if I draw, let's see, I'm going to do a little bit of fixing of my diagram. If this object ends up at this new position, 0.2 meters down the plane, then it will have fallen this distance y. So I'm going to redraw that triangle into a single triangle. This is 37 degrees. This is 0.2 meters. So that means I can figure out this height y from trigonometry. Y is going to equal 0.2 meters times the sine of the angle because it's opposite. So, um, so I now know the value for y. Plus any work done. And since this system has friction, it's going to have work. So, oops, I shouldn't really write it there because this is E2 here. I should write it when I use this equation over again. So I can say that E2 is equal to E1 plus work done. So now I can put in what E2 is equal to, 1 half kx squared plus mgy um, equals 0, coming from here, 0 joules, plus any work done. So now let's go ahead and figure in these values. Well, one thing to say here, important, let me calculate y here real quick. Y is going to be a negative value because it's going down from my original origin. My origin is where my potential energy, my gravitational potential energy is 0. So I need to treat this as negative 0.120 meters. So that means this equation is going to become 1 half times 100 newtons per meter times the distance squared, 0.2 meters, plus the mass of the object, 2 kilograms, times the gravitational acceleration, times the displacement, the vertical displacement, which is minus 0.120 meters. And all of that is going to equal the work done by friction. Why? Because when the system is done, um, all of that energy has been dissipated somewhere. It's either stored, it's stored in the spring, or it's dissipated in friction. So let's see how much energy friction dissipated by doing this calculation. So the system has lost 0.35 joules, and that energy has to go, um, is dissipated as work due to friction. So we have to find the coefficient of friction in this problem. And so we're going to use work to go from work energy to force. So remember that work is equal to force times distance times the cosine of the angle in between them. In our problem, the object is moving down the plane. The frictional force would be up the plane, and therefore the angle in between them would be 180 degrees, which would be a cosine of -1. So this is going to then equal the frictional force, which is equal to mu times mg cosine of theta for an inclined plane, times the distance that it travels, times the cosine of the angle in between them from the relationship for work. So let's see, how many of these things do we already know? Well, we know the total work is 0.35 joules negative, and that's going to equal mu times the mass, which is 2 kilograms, times the acceleration of gravity, 9.8 meters per second squared, times the cosine of the angle of the plane, 37 degrees, times the distance that the object travels, which is 0.2 meters, and the cosine of the angle in between the two objects. You'll notice that this is a value of -1, so this -1 and this -1 are going to cancel out and leave me with a positive value for mu. So if we now solve this equation for mu and do the calculation, we'll get a value. So we get a final value of 0.112. No units. Remember that the coefficient of friction is a unitless quantity. So there we go, solutions to the last two problems, and I hope that's helpful.